you very much. I'm going to talk about sort of the next generation VAEs that is going to be combined with flows in a framework which we call SurVAE Flows in an attempt to catch up with GANs, I guess. And so the story behind this is that a student from the Technical University in Denmark called Diederik Nielsen was visiting the University of Amsterdam under the Alice exchange program. It was actually the first student that did an exchange with the Alice unit in Amsterdam, and I thought it was very successful. So we started working together with Priyank Jani, who was a postdoc in Delta Lab, and with Emil Hogeboom, who was a PhD student, who is a PhD student in also in Uwe Bosch Delta Lab. And together we set off to combine flow models and VAE models. And if you want to learn more about Alice and how to engage with Alice, please visit the website at alice.eu. So in the first part of the talk, I'm going to do a very non-technical introduction, basically some kind of sort of background philosophy on machine learning, and so what I think are important directions in preparation for the later part, part two, which is actually far more technical and has lots of equations in them. So let's basically discuss first the very core of machine learning. It's one equation. It basically says that you combine inductive bias, basically expert knowledge, together with data to make better predictions. But there's a modeling spectrum. On the one end of the spectrum, we have generative models. You can think of them as inductive, models which are loaded up with inductive bias and lots of domain generalization, which I'll discuss more. And on the other side of the spectrum, we have discriminative models, mostly deep learning, where actually we need lots and lots of data to train them, and sort of they are you have a limited domain in which they function. But once you can train them on all that data and on that limited domain, they work spectacularly well, as we have seen over the past years. So let's first discuss a little bit discriminative modeling. So here's the sort of standard sort of data set that we use, digits from MNIST, and the idea is that we take the raw pixel values, which is here the sort of the pixels of this image, which is the raw sensor data. We put it on the input of a neural network. We push it through layers and layers, these days hundreds of layers of millions, if not billions, of network connections with all trainable parameters. And then at the end, we make a prediction. So we make a prediction about a property of the input. This could be, in this case, the class, but it could also be the style or some other high-level abstract property of the raw input. Sort of there's, this domain sort of where this works spectacularly well is deep learning, which is the type of models that we're considering. Speech recognition, it sort of started in speech recognition around, what is it, 2009 or something, where the first models started to work really well on speech recognition, and a couple of years later they were on your phone already. Machine translation is another topic, another domain where it works really well. Image segmentation and classification and object detection, very important for self-driving cars. And another one here, which made it into Nature, I think, is melanoma detection, or in more generally skin lesion detection, where people took a pre-trained neural network and sort of fine-tuned it on skin lesions and got very good results to predict, whether something happened to be a melanoma, in fact, better than the best physicians at that point. So deep learning, of course, got Yasha Banjo, Jeffrey Hinton, and Jan LeCun the Turing Award in 2019. As I said, it works extremely well on a well-defined domain in which you can collect many examples. It's responsible for 90% of the progress, and investment in AI at this point in time. It has generated enormous business potential. So big internet companies, but many companies actually have leveraged deep learning in their products right now, and it's producing a huge business potential. But in the academic community, there's also doubt whether this will be the final answer. The question is, will it be, scaling this technology further with more data and more compute power, and sort of making sure that so you basically build a big differentiable computer. Will that actually solve AGI, right, the artificial general intelligence problem? Will that produce intelligence which is close to what humans can do? And there's a lot of skepticism. And in some sense, the community is divided into sort of two camps in some sense. There is the camp, which you could call the Kirk camp, which is sort of leaning towards deep learning and differentiable computing, where in sort of it has an analogy with the brain, which is sort of the fast recognition, sort of the bottom-up sort of neural network kind of recognition. You could sort of argue is sort of the intuitive way in which we think. And then there is the slow thinking in Daniel Kahneman's terms, which is more like Spock, which is uses symbolic AI and logic in order to reason. And sort of these two camps sort of debate whether either deep learning technology is enough or we need really something more. Now let me give you at least a few examples of why I think we're not there yet. I don't know whether deep learning will actually in the end be able to solve all this, but there's certainly issues, things that we cannot really do yet very well using our current technology. And let me just give you this first example, which is sort of one-shot generalization. So here's a training example on your left. It happens to be a sort of a little tiny animal called a water bear. So this training example. Now here you have 3 test examples, and you need to figure out which one of these is actually a water bear, right? And computer algorithm, a machine learning algorithm, is spectacularly bad at this because it only sees one image, where humans are very good at this, right? I mean, I don't know if you've tried it. The first one you might be very very confident about. The second one you might be very confident about. That's certainly not a water bear. Third one you might be a little doubtful about, but most of you will probably get it right. And sort of this is the answer. So how do we do that, right? That's the big question. And it has a lot to do with the fact that humans have a lot of background knowledge. So we don't just train from these pixels, we embed that information that we see into a lot of background knowledge. The laws of physics, the laws of biology, laws of causality, psychology, sociology, what have you. All this background knowledge is featuring into a model that we sort of construct on the fly in order to sort of create, say, well, this is a little animal. I'm seeing sort of a little mouth in front, maybe 6, legs, and So we sort of classify all these things already into categories that we already know. There's also compositionality, which seems a very important part of models. I don't think neural networks do this very well, very effectively right now. But there are neural networks like this neural module network, which is trying to incorporate these ideas, which is where you sort of you train reusable blocks, a block for detecting redness and and aboveness and all these kinds of things. And then for any particular problem, you sort of compose these blocks like Lego into sort of a network on the fly very quickly to reason about a scene. And in fact, causality also plays, I think, a really important role in generalization. And of course, this was also, a Turing Award in 2012 by Judea Pearl. And the idea is that if you understand the causal mechanisms of the world, you can sort of train one of sort of these modules and then apply them somewhere else in a completely different context, because the sort of the causal relationships are preserved if you move them from one context to the next context. And if you just train correlations, then that's much harder or impossible. And maybe this is a very interesting quote from Judea Pearl that I want to read. It says, this ingredient, by which he meant causality, should allow computer systems to choreograph a parsimonious and modular representation of their environment, interrogate that representation, distort it through acts of imagination, and finally answer what-if kind of questions, right? So we have some kind of model that not only makes predictions in the real world, in fact, we can imagine new worlds which don't even exist and answer questions in those new worlds. And this idea that we can imagine worlds is very, very powerful. So in machine learning, we are also building on these ideas. Of course, causality is a heavily researched topic, but sort of slightly more general, maybe we can look at generative models, or in science often called forward models. And a generative model is a model that simulates the data generation process. And it's sort of this nice simulation here about two galaxies which are colliding is, I think, a beautiful example of it. It just uses the laws of gravity. It has, well, very few parameters, if any, and you can sort of get beautiful sort of simulation of the world. So it's a very simple model in some sense, and that's one of the core ideas, is that forward models are in fact a lot simpler than these inverse models that we tend to train using sort of machine learning. Now, what are the type of forward models that we entertain in machine learning? Well, we have simulators. Ordinary and partial differential equations are also simulators of some kind. In the old days, before the deep learning hype, we were doing graphical models, and you see a few here, which are also generative models in which you can reason. And then nowadays, the more modern version of that is called probabilistic programs. And then, of course, so these are fairly explicit models where we embed a lot of the actual knowledge into the models. It's what we call, like, traditionally call actually modeling. But there's also forward and generative models these days that are completely trained from lots and lots of data. Here is, again, very successful model to generate really amazingly sharp and realistic images. I wouldn't have thought this were possible 10 years ago. And the idea of course, as most of you know, is that you collect a training set, and then you build some kind of generator, which is this box here, to generate images of dogs in this case. You also train a discriminator that that tries to discriminate between images, real images from the training set, and generated images from the model. And sort of the discriminator and the generator are sort of trained against each other in some kind of arms race to get better. And in the generator, if it wants to keep fooling the discriminator, it has to get better and better. So now, if you look at this particular set of dogs, one of these dogs is generated by a machine, by an algorithm, and it's just, I wouldn't be able to tell it, but it's this dog, and I think that's an amazing result. Okay, so in the sort of the world of generative modeling, there's also another class of models which I fancy variational autoencoders. So that's written here. So there we have an explicit encoder, QZ given X, which produces a code for some sort of blurry or sensor data. It produces a latent code which represents the properties of this 8. And then we have also a decoder which then sort of simulates or generates things which you can see on your sensors, which could again be the pixels of an image. And so, and in the sort of scientific literature, these things are often called a forward model, or this is our decoder or channel, right? And then there's also the inverse model or the encoder. And inverse modeling is like a huge field, in fact, in the sciences. So how are these two paradigms related, right? We had discriminative modeling, which sort of deep learning was a prime example. And then we have generative modeling, in which variation autoencoders and GAN and simulators are examples. So how are these two things related? Well, very simply, they're related through Bayes' rule, right? In the forward model, we have basically our probability of data given class and other properties times a prior over classes and other properties, and then normalization factor. And we all know that Bayes' rule produces the inverse of that, which is the discriminator or the probability of the class given the data. So these two things are very strongly related, of course, to each other. Now, some pros and cons. The white box approach, the generative approach, it's very data efficient because you model, you incorporate expert knowledge like the laws of physics. It's highly interpretable. Because the variables that you write down, say in a graphical model or a simulator, they all mean something in the real world. And it is better at generalizing because often, you put the causal structure in these models. And of course, you put a lot of prior knowledge in them, so they generalize better. The deep learning model they're much more flexible. There's like billions of parameters in these models. And in some sense, they overcome the limitations of the human imagination, right? Because, you know, you can imagine certain laws of physics, and maybe in physics, in elementary physics, this works out. But, you know, if you try to model the internet, that will not work out, and you will be limited by your own imagination. These deep learning models overcome this human bias. They're super accurate, you know, it's basically a empirical fact now. And also, you know, you model your predictions directly, so you model them in the direction that you actually want to use your system. And in the white box, you have to use Bayes rules. You have to explicitly invert it if you want to use it in that direction. And they're also fast because we don't need to use Bayes rule, and we have, you know, GPUs now to sort of help us do these predictions really fast. But I would claim that we want to sort of combine these two worlds into sort of one modeling paradigm. Now, in a sense, this is sort of how the world looks like in terms of generative modeling with deep learning. We have GANs, which is basically by far the biggest research area. We have VAEs, and I haven't discussed this yet, flows, but I will discuss this in a minute, which is another sort of class of generative models, which people use a lot now and is increasingly getting more popular to do generative modeling. And if you want to read a little bit more about sort of my vision on these kinds of aspects, I invite you to look up this particular blog. And if you want to search for it, you want to see as far as the AI can see. If you search for that in my name, you'll find that blog, and then you can read a little bit more. The link is also here if you see the slides. Okay, so now we are at sort of the second part of my talk, which is, as I said, a lot more technical. And so I hope people can stay with me for this part too. So let's first explain in a little bit more detail the variational autoencoder. So in the variational autoencoder, we have some latent variables P of Z, and we have a prior over those P of Z, and perhaps so these are unobserved, and perhaps we also have some observed class labels P of Y, and we can sort of generate by drawing a Z from this prior and a Y from this prior, and then sending them through some kind of neural network. This could be just a completely deterministic neural net to generate the parameters of a probability distribution P, which could be, say, a normal distribution, from which we generate the actual sensory values X, which could be the pixels of some kind of image. Okay, so that's a generative model. And then the inverse of that, so the idea is that we're going to model the inverse of this. So this is the decoder, and then the encoder model goes in the opposite direction, where we give it the actual pixel values X. We again send it through a neural net. We again predict the parameters of a probability distribution from which we can then sample latent causes, you know, like style or whatever, sort of some abstract feature of the input, and from there perhaps we could predict the label. Now in equations, this looks like we are trying to minimize the KL divergence between two terms. The first term is basically this term here, which is the probability of the data. This is the empirical distribution of the data times the probability of the latent variables given the data. So this is the encoding distribution. And on the other side, we have the decoding distribution, the generative distribution, where we have a prior over latent variables and then a distribution over X given Z. Now you can decompose this into two terms. And you see that if you learn the parameter of your encoder and the parameters of your decoder, and basically what you want to end up with is that the distribution P, which is your model distribution, becomes equal to the empirical distribution. Well, not exactly, because this is a bunch of delta peaks, but close to it. Or if you could put here the actual data distribution, then this would be fine. And the Q, the encoder distribution, should converge to the inverse of the generative model. So this is Bayes rule, obviously. So the Q should basically become P of Z given X, which is the inverse of the generative direction. So this all makes sense. So if we minimize this, we'll be fine. Of course, this term is intractable, so we have to bound things. Oh yeah, so we can also replace our deep neural network with a simulator in the decoder direction. Okay, so then, so let's go to that equation for the expression that we had for the VAE. So that was a KL. Now we can work out the KL, and we can throw away all the terms which are intractable, and then we get a bound on the marginal or the log marginal likelihood, or the marginal log likelihood, whatever it's called. So it's the probability of the data marginalized over the latent variables and then taking the log, and that's larger or equal than the okay, so the expectation, I guess I shouldn't have put the sum here, but the expectation over Q of the log of Px given Z times the P of Z, which we can call sort of the minus energy, and then minus or plus the entropy term here, which is the entropy of the encoder distribution. And this is very much like a free energy. So this is the first way that people would write these kind of things. And we sort of say, well, this is like minus the free energy, which is the energy minus the entropy. And this is something that people know very well in physics as the free energy. Now you can also write this differently. And that's sort of later people started to write things like this, which is exactly the same, where you sort of move the P of Z into this term and turn it into a KL. And then this is, people think of this as the reconstruction error. How well can you reconstruct X given Z from Z? And this here is the complexity term, which says how different is my encoder from my prior. If it's very different, the model is complex. And if it's not, if it's the same, then it's not very complex. Okay, and then there's one way to sort of rewrite these terms that is left that we haven't done yet, and that's the one I'm actually going to use in this talk, which is, now let's put the prior here in its own sort of expectation box, and we're going to put the P of X given Z and P Z given X here into one expectation. And so, and the way we're going to interpret this in the next couple of slides is like a reparameterization of our density. So we have a P of Z and we have a P of X, and we're gonna say that we're gonna reparameterize X in some new variables Z, and we're gonna do that stochastically through an encoder distribution. And then the term that has to compensate for volume changes and things like that is going to look like this. Okay, so I'm going to expand on that a little bit, and I will expand on it by actually first talking about normalizing flows. So in a normalizing flow, the idea is literally to write your P of X in terms of a reparameterized Z. So now X and Z have the same dimensionality. There's a deterministic function, Z of X, between them. And then there's the reparameterization equation, which basically says I can write my log P of X as my log P of Z, but I have to include this Jacobian term as the log absolute value determinant of this sort of derivative matrix, which is the Jacobian. And this term precisely sort of compensates for any volume changes that happen when I move from X to Z. And the idea of this paper was that you can stack these things. So you can say, well, let me make sort of X the sort of last random variable in a chain, and let's rewrite this whole thing basically as a series of transformations. And then I basically can write the P of X as the P of Z, which is the variable at the very top. But then I have this sequence of Jacobians that I have to incorporate. And then you can backpropagate through this whole thing in order to train, make this a very simple function and train this bit here so that you can simulate, a model that looks a lot like the data distribution. Okay, another sort of set of models which people use in order to do inference and model the world is a Markov chain Monte Carlo. And in Markov chain Monte Carlo, you basically look at a quantity which is called detailed balance. And in detailed balance here, you're going to say something like, okay, I have my probability P of X of some state X that has a certain probability. The size of the sphere indicates what the probability of that state X is. And I move some of my mass to a probability P of X prime here. And let's say there's a higher density here, right? And then there is and in that same kernel, we also move some of the mass back. And we are going to run this Markov chain until it is in equilibrium. And that basically means that this pile and this pile are not going to change anymore. So the amount of mass here that I'm moving here is precisely compensate for the amount of mass that's flowing back here. So this is the detailed balance equation. And if you have detailed balance everywhere in your space, then you can show that the samples that you're drawing are actually drawn from the correct distribution. So if we rewrite this and add some logs and say X is, xt plus 1 is Z or something like that, then you write this. So you say log p of x is log p of z plus the log p of x given z divided by p of z given x, which is of course just log of base rule. So it basically, it basically also says that this term here compensates for sort of how much mass are we moving around here, right? So we cannot just write this equal to this. We have to compensate for the fact that we are moving more mass here and there. Okay, so now let's put all of these three things that I've discussed together in three equations, right? And look at their sort of similarity. So for normalizing flows, we wrote this equation where this was the Jacobian. Now for Markov chain Monte Carlo, we basically wrote base rule, where we have, it's the first two terms are exactly the same, and then we have a log of this term here. And for the ELBO of the variation autoencoder, we wrote this term. Now it's a bound. Here we get an expectation, and here we also get an expectation. And now we have P over Q instead of P over, this P. But if Q becomes equal to P, then in fact, these things become the same. And so basically, I'm just claiming these are just three sides of the same die, if you want. And you can turn this into a little algorithm that goes layer-wise and computes the likelihood of something. So let's say I have some data X, I have some probability P of Z, I have some function F, deterministic function, right? And for T iterations, if F is a bijective map, then I can sort of sample or get from X get my Z. And then in that case, I compute this thing here. But if F happens to be a stochastic map, like an encoder Q, then I sample Z from my Q distribution, and then I have to include this term here, so this term basically, but then without the expectation because I'm sampling one sample. And then I'm taking this term. Now at the end, I'm just collecting all of these terms together. And this is a direct generalization of the sort of iterative normalizing flow, where we can now start to combine stochastic maps as well as deterministic maps. Now, from that inside, we realize there is a generalization of this too, which is what happens if it's not a bijective map, if it's not a stochastic map, or in a stochastic map you sort of map from one point to many other points. But what if it's a surjective map? And we have two types of surjective maps. One that is surjective from Z going to X, so you go from 3 points down to 2 points, and one going from Z or from X down to Z. So now sort of you go from your input space to a lower dimensional latent space. And so you can study all these things, and it turns out, so now we have 4 instances, and sort of each one could comprise a layer in this kind of stacking architecture, this deep architecture that we can build. So if we have a bijective deterministic map, we have F and F inverse, and we have the sort of the Jacobian term. If you have a stochastic map, we have an encoder and a stochastic decoder. We have this term here, but we make a little error, and that's the error that we're making. If we have a generative surjection, then X, from Z to X is deterministic, backward is stochastic, and it turns out that we can actually, you can sort of write this term and take the limit, and you get some explicit expression that I'll show an example of. You still make an error, but if you have a surjective in the inference direction, the surjective map in the inference direction, then you get 0 error, and you can also get sort of you can also compute these Jacobian terms kind of explicitly. So we've now sort of generalized this concept. Now let's look at 3 examples that you may already know. This thing is a little bit in the way, so let me see if I can. Okay. Oops. So so here we have a map that you can call a slicing map. This is already in the literature. So you go from X to Z. So there is a sort of a deterministic function between X and one part of your Z's, and then there is a stochastic map from X to the other part of Z. And then, of course, when you go from here to here, you can sort of make it a deterministic surjection. There's also, you can also do this in the opposite direction, of course. And then there's sort of this maximization operation that people use, for instance, in pooling, where you take a bunch of X's and you pick the maximum value among those X's and you turn them into Z. And then there's a whole bunch of other things in X that sort of get forgotten in some sense. And so if you go in the opposite direction, you sort of move your Z into one position here of X, and then you have to randomly generate the other x's in such a way that they are smaller than the x that you made the maximum. Okay, so you can sort of look at this table and you can sort of write all of these kind of operations and the terms that you'll have to include in your likelihood calculation. They're all very explicit terms that you can then calculate. And this way you can also come up with sort of new layers, like a sort layer, an absolute value layer, for instance, that sort of we experimented with a little bit. This thing generalizes a whole bunch of stuff in the literature. Now, I even forgotten things here. I recently learned that there's also something called stochastic normalizing flows that we don't, by the group of Frank Noe, that we didn't put into our paper, but we'll put in the next one, in the update. So these are all kind of architectures which have been proposed, and you can now easily think of them as, an instance of this SurVAE flow architecture, right? By basically thinking of them as a stochastic map of a rounding operation or bijection of a slicing operation, et cetera, et cetera. So now, in some sense, once you understand SurVAE flows, you sort of understand all of these papers in one go. It's kind of nice. So what I would really like, but I realize this might be a little bit of wishful thinking, is that now that we have defined SurVAE flows, and SurVAE flows is just a framework that seamlessly sort of generalizes flows with VAEs into one nice framework, that SurVAE flows might become competitive again with GANs. So I hope you would be also, experimenting with this technology. So then to conclude, as I said, SurVAE flows sort of unify normalizing flows and VAEs into one nice framework. And we will actually, Diederik Nielsen, who is of course the main contributor to this project, he will produce nice code for you too, so that you can start playing with it. And so surjections are actually genuinely new operations that sort of a new type of layer that's deterministic in one direction, in the surjective direction, and stochastic in the opposite direction, and for which you can actually compute exact contributions to the bound, and sometimes in one direction actually the bound is tight. So if you want to keep one thing in your mind today, the takeaway is flow plus VAE is SurVAE flow. And thank you very much.
Okay, thanks very much, Max. That was really interesting. We're going to move on to some questions now. So I can see there's already a couple in the Q&A. If you have more questions, please post them in the Q&A, and we will go through them. If we read out your name and you would like to read out your own question, then please just raise your hand in the Zoom chat and we can unmute you and you can ask Max the question yourself. So I'm going to pass over to Daniel now, who is going to lead the Q&A discussion. Thanks.
We can't hear you, Daniel.
Okay, thanks. Sorry about that. I couldn't unmute myself. So I guess I'll kick it off by asking a question. So thanks very much for an interesting talk. You had these three sort of paradigms for thinking about generative models earlier. Maybe you could go back to that slide. You had the VAE way of thinking about things. You got the MC way of thinking about things, and you said that these are three sides of the same die.
So this one, can you see this slide, or am I not
still on
sharing?
your conclusion slide?
Sorry, on my conclusion slide?
Yes, at least I am.
Oh, okay. So I guess I have to sort of share full screen or something, maybe. This? Can you see this?
Yes, we can see
Okay.
that.
Okay.
So I think it was one slide on from this. Or maybe two. You've got one where you have a Jacobian.
This one, yes.
This one. So I was wondering if you could just give a bit more intuition behind what this log sort of decoder on encoder term is, because is that measuring like a change in volume of your probability space, even though you're making jumps between spaces of different dimensionality?
Yeah, so I think that's it certainly, I interpret it as the generalization I sort of I view this here as a generalization of this, and clearly here you have the opportunity to change dimensionality, but you do need to compensate for this term, and the way I sort of think of it as, maybe I guess this is now in front of this. Let's see. So the way, maybe the easiest way to think about it is this way, where you can sort of say, you know, here's a random variable x and here's a random variable z, and so you can sort of think of moving mass in some sense by some transformation, but then in order to sort of, so this might, because you're moving mass, you might move a lot of mass in this direction, and I guess you have to compensate by the inverse sort of movement of mass to sort of, yeah, get base rule back of some kind. So it's, yeah, and so this picture for me sort of describes a little bit how, you know, in the MCMC framework, you can understand transforming from one point to another point, and that is the analogy of, you know, if this were a deterministic system, you would then, instead of having this p thing, you would have deterministic functions, and you would have then the Jacobian, which would sort of, you know, would be the volume change that you were making. So if you would take an infinitesimal point and you would blow it up under that map, then, you know, your density would sort of go down, right? And then you would have to compensate with that Jacobian. So this ratio between this p and this p precisely sort of fulfills that role of, you know, this expansion and contraction.
I guess this is a very useful mechanism. So now you can jump between spaces with different dimensionality. So you have a much more flexible way to build flows.
Yes, so exactly, that was exactly the point, that there's a couple of things that are nice about stochastic sort of transitions. One of them is that you can go from one point to sort of 2 points. So you can sort of do multimodal things in a way, right? And so you don't have to, things don't have to, in probability space, things don't have to connect sort of through smooth sort of transformations. And the other one is that makes it a lot more flexible now, is that you can change dimensionality as you go through the layers. Of course, the VAE already had that, but now sort of the idea is that you can combine these layers together in multiple ways.
Okay, I think I'll ask one more question, and then we have a few more in the side panel here. So I'll ask one of those just after this one. This is more of a high-level question. You were talking about inductive biases right at the very beginning, and how you have this sort of spectrum of different kinds of models you can have. So on the one hand, you have these white box models where it's lots and lots of expert knowledge. And on the other hand, you have all of this sort of black box sort of thinking where we just learn it from the data. We just do the Google thing, we collect enough data, throw enough GPUs at it, and job done.
Yeah.
Where would this model sort of sit within that thinking? Because to some extent you have an bias, but it's not
really
much. It's not. It's a lot, but it's not really like my physicist writing down the laws of physics into my model.
Yeah, I think that's a very fair point. So in a way, so it sits as like this. So I think if you have a lot of inductive bias, you should be able to put it in a decoder, right? So if the decoding model is the place where you can sort of collect your prior knowledge into that, it could become a simulator, it could be something. But in the absence of that, you can also, of course, make it a neural network. But I'm just claiming that in some sense, that network has an easier job because it models things which are more natural and easy to learn than the inverse model. For instance, in that direction, you expect causality to hold. In that direction, you expect the laws of physics to hold. So in a way, you can train a neural net with lots and lots of parameters, but in some sense, that's the more easy direction to model. Of course, it's harder maybe because you explode the dimensionality. If you go to an image, of course, you know, you have to generate images. So in that sense, it gets harder. And of course, the encoder is a model which has lots and lots of parameters, which is the difficult but useful thing to train. So I would say, if we get good in generative modeling, then you can still say, okay, I'm going to use my generative model to help me build better encoders or deep learning models. So you can think of that as some kind of perhaps regularization on your encoder model, because they try to be each other's inverses, and because the decoder model is the more natural sort of channel model that's easier to learn, that follows the laws of physics and causality. If you can train that well, and you say that the encoder needs to be the sort of inverse using Bayes' rule of the other one, then so you can regularize your encoder a little bit. So that's one way to think of it. But even better would be if you do have a lot of knowledge about your generative structure, about a prior knowledge, like maybe you understand your channel, or you understand your sensor or something like this. So then all that information can actually be put into your decoder model.
Okay,
So
I guess what's really interesting, or maybe what's going to happen in the next few years, which I think will be super cool, is if you can use these sorts of ideas inside scientific simulators, which scientists have been building for the last, who knows how long, 50, 60 years. That would be super interesting.
Yeah, I think, yeah. So what you see in the sciences actually is that, more and more, so, or also in engineering actually. So people write down models that they know and love very well, which are based on engineering ideas and physics. But those models have very few parameters. But then you start to see that they are going to put sort of bits and pieces of those models and sort of add parameters to them. So they're going to say, well, let's make that a little bit more flexible. Let's make that a little bit more flexible with some parameters, and just train up these parameters. And so they slowly migrate away, from the physics model or the engineering model, and depending on how much data that they have. And then you can actually do the same thing as well in your inference model. In your inference model, you might have sort of an inference algorithm which fits the sort of the decoder model, which is just some classical sort of inference algorithm or inverse model. And then you can also put parameters around that model and make it more neural in some sense. So you can seamlessly sort of interpolate between the classical models where you don't need a lot of data and you can put a lot of prior knowledge in, and sort of the more neural models where you need a lot of data, but they're also far more flexible.
Okay, I'm going to move on to some questions from the audience now. So I was wondering if Ira Korshunova could ask their question. So I think someone's going to unmute you, Ira, and then you can ask your question.
You should be unmuted now if you want to ask the question, Ira.
Well, we can read it, I guess. It's right here.
Okay, I'll read it then. There have been recent papers on augmenting normalizing flows where inputs are concatenated with extra noise dimensions. This is done to tackle the bottleneck problem of normalizing flows.
Right.
But by doing so, we no longer can compute the exact likelihoods. Are SurVAEs also generalizing augmented normalizing flows? What would be the benefits of SurVAEs over augmented normalizing flows?
Yeah, it's a good question. So an augmented normalizing flow is one example of a SurVAE flow. So maybe I can see if I can get back to that thing here. So I think probably one of these things here is an augmented, isn't this augmented normalizing flow, A and F here? Yeah. So basically, these are just the idea is that you can think of this in a more general framework. So you can think of this as, you go from X to X times noise variables epsilon, as you described in the question. So that's an augmentation step. And then there's a bijection between this one and this one. So you can just think of this one as a layer and this one as a layer in a SurVAE flow, and then do backpropagation on this thing. So in a way, it is literally, unifying a lot of these different things, and for me that cleans up my brain nicely, so that I can actually, think of this as one framework, and I start to model things more freely. And the code that's being delivered by Diederik will support that kind of process kind of nicely.
Okay, nice. I think we got a question from Jose Henry Leon. It's Jose Henry Leon on data efficiency. Ira says thank you, by the way.
So Jose, please raise your hand if you'd like to ask the question yourself. Otherwise, we can read it. Okay. So you should be able to speak now.
Hi. Yeah, my question is very simple. How this new paradigm, variation of autoencoders and normalizing flows will manage to be data efficient?
Yeah, so in general, they are not more data efficient than a VAE or a flow. But sort of going back to the first part of the talk, my sort of the idea is that you can become data efficient if you can put prior knowledge in your generative direction. So if the decoder side of things, if that's something where you can put a lot of prior knowledge in, then you become more data efficient, because the encoder and the decoder are tightly coupled in this scheme. So the encoder will then be directed and guided by the decoder, and the decoder you've put a lot of prior knowledge in. And it's only in that sense, in a more sort of abstract sense, that using generative models is a good way to become more data efficient, but only, of course, if you know something about the data generating process that you can put in there as a prior.
Okay, thank you, Jose. And we have another question from Nick Walker on maybe shifting the focus a bit to the kind of data domains. So looking at text. That's
Yes,
Nick Walker.
If you raise your hand, if you would like to, okay. There you go, you should be. Sorry, I think we're both muting and unmuting at the same time. You should be able to speak now, I think. 1 second.
I think I've already read the question 3 times, but.
There you go.
Okay, I've been doing quite a lot of work on hierarchical autoencoder VAEs for text. So is this, do you think this is relevant to text? I mean, there's lots of problems with text because, for example, you can't really do a GAN because you can't flow the gradients back from the discriminator network. And so the choice of the max on your logits causes quite a few problems. So are these relevant here at all to text?
Yeah, I think so, because if you manage to use a VAE on text, then what this can do for you, for instance, is you start with a VAE to basically go from X to a latent space Z, but then on Z space you can sort of stick a a flow to basically model your prior P of Z in a way with another layer of sort of latent variables. And flows have certain advantages over VAEs because they're not noisy, right? They are deterministic, and so learning is the variance in the gradients is less. So then that part, once you have moved to sort of continuous latent variables using your VAE, you can then model that sort of effective prior P of Z in your VAE with the flow. And I mean, that's not a new idea. That's somewhere in this kind of set of ideas is probably there. But I would certainly say in this more general framework, you can sort of now start to play with this. You can say, okay, now I have, a VAE for my first layer, but now let's add sort of a couple of sort of flow layers on top of it and just treat this as one thing and back propagate through the whole thing in this new framework. So I would say certainly, and this might actually be a very nice application area where GANs can't work really well, and these types of models can work very well. Thank you.
Thank you.
I think we have a question from Hamad Somro on biases in models. That's Hamad Somro.
Yeah. He doesn't have his hand raised in the chat, so I think go ahead and ask that one.
Right. Don't human models suffer their own biases, no matter how much they try to be fair in the model? So I think basically what Hamad's getting at is the fact that if you build an inductive biases, it could still be wrong.
Yeah, that's very true. So let me go back to my very first slide, actually. Well, second slide, I guess. Okay, here. So this slide sort of tells that story. So it says that there is a trade-off, right? There's a scale here, so there's a trade-off. So if you have a lot of data and you're interested in testing or using your system in the domain in which you have collected all that data, then just forget about your biases or forget about human engineering models or putting priors in. Just train this thing with lots and lots of data, right? Because your data will see, there's more patterns in your data that you can uncover using your deep neural net than you can possibly put in with your human imagination. However, sometimes you don't have all that much data, or you're in a corner of space, you know, where you don't have a lot of data, or you want to take a model outside of the domain where you have data into a new domain. Right? Just think of, you know, some kind of, you know, detector that figures out, you know, who causes accidents in a country, right? And you train this in one country, like in England, and then you want to apply it, you know, in another country like Japan, right? And so you want to get at features which are not just correlations, because maybe in England, you know, black cars get into a lot of accidents. That's a correlation. But in maybe Japan, red cars get into a lot of accidents, right? But if you uncover the underlying sort of causal structure, which you could think of actually as a real model of the world, which could be, you know, what guys make most of the accidents, and what about guys, you know, is predictive of making accidents, right? Maybe their testosterone levels or something like that. So if you put that into your model as a causal model, now that's bias, right? It's human bias, but it is the type of bias which will actually allow you to generalize from England to Japan. And so it's always, in my opinion, it's the most important equation of machine learning, which is exactly this balance, this scale between how much, you know, do I trust my data, how much do I trust my inductive bias, and it all depends on how much data do I have and how far do I want to generalize away from the domain that I've trained my model in.
I guess what's kind of interesting is that you mentioned this sort of this trade-off, but there is a very very formal sort of way that people have been able to do probabilistic reasoning, which has been developed over the last 20, 30 years, which is the sort of the Bayesian school of thought. And you didn't mention that at all in this talk, which I thought is kind of interesting. In fact, I think all of the models you presented are trained with maximum likelihood.
Yes, yes.
So I wonder where you see the sort of the Bayesian side of things. Is it just a tool which we no longer need because we have enough data, or, you know, will it make a comeback, or is it missing from this work, or is maximum likelihood enough?
Oh, for this particular application, definitely Bayesian is sort of a different dimension, right? So I would think if you think very hard about generalization performance and about predicting uncertainties and all these kinds of things, that's where Bayesian becomes extremely attractive. Even though I talked about Bayes' rule, that's certainly not, you know, Bayesian statistics in the sense that there we put probabilities on parameters of our model and structure of our model. So for this particular talk, you know, it's just fine to sort of think about maximum likelihood and, you know, trying to fit strong models. And also in the frequentist world, of course, there's lots of ways in which you can protect yourself against overfitting. You can do cross validation, or you can put other kind of sort of regularizers there that sort of, you know, try to avoid the overfitting. So I think in whichever world you live, you know, you can sort of get similar performance. You know, some people like Bayes a lot, myself included, because it's clean and it's easy to understand. But I think it's sort of, I mean, it certainly ties in a lot to this discussion, right? Because in some sense, what Bayes will tell you is how to set the scale. It will tell you how much should you rely on your data, and how much should you rely on your inductive bias, and it will basically automatically balance these things out. It will basically trust your model to the extent that it is supported by the data that you have, and it will provide uncertainties for the part of the data where you can't trust your model. And then you can do two things: more data or more inductive bias in some sense to reduce that uncertainty. But yeah, that's certainly a good comment.
Okay, so we've only got 2 minutes left, and I've got a page full of questions which I'd have loved to have asked. But maybe we should just sort of end on a slightly easier one. Why should I not use a GAN?
Right.
Or maybe not so easy.
I don't think it's very easy, and I think both have their merits, and sort of again, and sort of this framework that we're. So if you need a likelihood, for instance, you need it for compressing your source data, or you want it for some other purpose, then I think these types of models are the way to go. If you are after producing pretty pictures, and I don't mean that in a sort of denigrating way, because there's lots of very cool applications in industry and wherever where you would really need sort of very beautiful pictures of things. Like you can imagine that you want to imagine yourself in a certain dress or in a certain trousers or whatever, and then if you can generate a picture with you in those trousers, that's certainly extremely useful. So I think they are sort of different application directions. Although I should also say that some VAEs have become amazingly good now also at generating pretty pictures. So there's DeepMind, I think, had sort of VQ VAEs and extensions of those, which are also extremely good at producing pictures which look amazingly sort of realistic.
I think there's a couple out today as well with some pretty incredible pictures which came out in the last 24 hours. If you crawl through Twitter.
Huh, good.
But I think, yeah, I think that's all we have time for, unless we have a few more minutes.
I think we will wrap up there. Daniel, thanks so much for leading the discussion today, taking the time to be here. And once again, Max, thanks very much for a really interesting talk. We will make the recording available on YouTube afterwards. So you can just go to our Machine Learning Meetup channel if you want to watch the talk again. And thanks everybody for joining. We look forward to seeing you at future meetups. Thanks very much.
Thank you very much for hosting this.
Thanks.
Bye.
Bye.